Hello friend, welcome to my YouTube channel Electrical Boost. In the last video we understood the BJT structure and basic operation. Today we will begin an important section, that is biasing of BJT. That is the biasing of BJT. In this topic or in this video we are going to cover why biasing is important, biasing is needed, okay, and in real circuit. Next we are going to what is the DC load line, what is the DC load line, okay. Next we are going to what is cover Q point, and we are discuss one bias method, that is called fixed bias method, okay. In this video we are going to cover this, okay. And in the next video we are going to discuss some different method of biasing, but first to know why the biasing needed. BJT is a, already BJT is a current control device, okay, but it does not automatically operate in stable condition. We know the BJT can control the current, but it cannot be automatically or amplify particular unstable region, so that we need to bias that one, okay, because the gain factor beta is changing with the temperature and some changes in voltage or supply, so that we need to proper bias for getting the proper output. If the transistor is not properly biased, the transistor may enter in cutoff or go into the saturation, okay. For amplification we need to in the active region only. If it will go in cutoff or saturation region, then it cannot useful, okay. So biasing mean the setting a stable operating point. Biasing means setting in a stable operating point, you can tell like that. Biasing equal to stable operating point. We are going to discuss what are the operating point, what is the, okay, the stable operating point is the called Q point, okay. Next we are discussing for good biasing ensure, okay. What the good biasing is do: amplify the output, not destroyed, switching is reliable, device remain in safe, okay, stable for over the any temperature, okay. Next we are start what is the DC load line. For the deciding the stable point, we first know what is the DC load line. Basically DC load line is the, you can check in the output side, it basically come under, when you draw one VCC by ICC, VCC means this one, okay, voltage drop, this one VCC, okay, this is IC, this is VCE. So take an example. If the transistor in off condition, that off condition means, when the transistor is off condition means that IB equal to 0, off condition, okay, IB equal to 0, that means IC also 0, okay. So the entire supply drop, entire supply means this one off means it is open, then entire supply, the VCC will equal to equal to VCE. VCE. Okay. Then another condition, one we taking as off condition, one if it's fully on. If full on condition, then full on means there it is just like short circuit, means that VC equal to, here VC equal to 0. Then IC, full on means IC is maximum, IC is going to maximum, IC equal to maximum. Then IC equal how much? Only this resistance, this is completely on means it will short, only RC is present. Then IC equal to VCC by RC. Okay, if we from this curve, from this we can take one point when the off condition, means that IC equal to 0, IC equal 0, VC equal to VCC. Okay, one point. Another point when VC equal to 0, VC equal to 0, VC equal to 0, this point. Then here IC equal to how much? VCC divided by RC. When you connect or join this point, two point, whatever you get, this is called, this line is called DC load line. DC load line. DC load line. DC load line. When the whatever the stable point is lying in this line only, DC load line, here is the called the cutoff region. This is the cutoff region, and here the saturation region, here the saturation region, and this is called completely active region. Here we know what is the DC load. Next we are going to know what is the Q point. What is the Q point? How it is lie in this point. Okay. For Q point, we can put the Q point anywhere of this DC load line. Q point. Okay. You can put here. You can put here. But we need to decide for our proper amplification. We need to decide a place on the DC load line so the transistor will operate normally, means that AC swing or AC amplifier properly it swing or minimum destruction or stable. See here, suppose I take here, I take this is as one Q point, suppose. Okay, suppose I take this is as one Q point. Let I take this is Q1. What happen? Suppose I take this one. Here what happen? This IC is high but VC is less. Suppose we are going to amplify, then what happen? When I give the signal here I giving the one signal, then what happen? Some part here it is clip, some part here it will be clip, some part negative clip is there. Okay, so that it is not some part a person is clip. Suppose I take here, then some section of this one also clipped. Okay, so that this is the middle center point is the perfect saturation point. Okay, so that when you select the Q point, you need to select like this, that is means VCC, whatever you taking the VCC by half, and whatever the IC or current you are going to take, this is IC going to half, IC going to be half, so that in this point only we can get proper saturation. But this Q point can be vary according to the dependence of IC. That IC we depend upon the gain and some other factor, so that we need to stable that point, so that is some different biasing method is there today we are going to discuss only one biasing method, that is called fixed biasing method. This is not practically used, somewhere only for the low cost toys and a simple test circuit we can going to use that fixed bias circuit. Here we can show the fixed bias circuit. You can see here, we can see this is the simple circuit for the fixed bias configuration. Okay, what the in the fixed bias is means, when suppose once you fix the design, when you fix the design, after that that cannot always fix one Q point, so that what happen when the some beta value or gain change by the temperature due to the some particular transistor or BJT, the beta will change with the temperature also. That time the Q point is unstable. That time Q point is unstable. So that this type of biasing method is not suitable for the practical. But from the basic, we need to know how it is stable, how it work. Okay, biasing. Suppose here only we connected the collector to one resistor and one is the base to one resistor, and here one, this is the emitter. Here we giving just connecting one capacitor. Okay, actually the capacitor for the decoupling or by decoupling capacitor for that output for this AC, for the AC input. Okay, this is the output terminal, this is the input. Okay, forget about this one, we just go faster. Need to set a biasing or Q point. Okay, suppose here we think first we know to decide what is the value of, for deciding the Q point, previously known. This is about that the curve, the characteristic, this DC line. Okay, the waste will occur when VCC by 2, when VCE equal to VCE means this one, VCE equal to VCC half of the VCB, and here the IC is equal to this one VCC by RC. So that for getting particular voltage, we need to know first, we need to decide what is the, from this value we can amplify. Okay, first suppose you take this example, this one BJT which having that gain beta equal to 100. You can see in the data sheet some are mentioned in the beta value, or you can see the ACF. Okay, this one also beta name, other name. Okay, the gain mentioned here. First we need to find this value, how to set this value to getting this Q point. Okay, first suppose here for example this VCC, we take that the VCC equal to 9 volt, so that the DC point come here, this is maximum 9. Okay, maximum up to 9. So that first we need to find what is the RC value. What is the RC value? For RC value, we first decide what are current requirement. Suppose we want to input something voltage, but our some circuit is required some 20 milliampere or 20 milliampere. For the 20 milliampere, we need to find this RC value. RC equal to what? RC equal to this voltage, this will 9 voltage, 9 volt. This one VC you know na already. Find VC at saturation point. VC equal to 9 by 2. This means 4.5 volt. 9 by 4. You take in 200 volt also. Okay, 9 by 4.5 volt. 4.5 volt. So that divided by 20. So that this will come 0.225 kilo ohm. You can take as 225 5 ohm. Practical this is not available. We can take 220 or 5 like that series in making the RC. Okay, for practical circuit. This is the RC value. For this RC, this much current only we can amplify, this much current. For this RC we need to decide what is the RB value. Then RV equal to this, RV equal to already beta, no, from this beta also you can find first IV value, then IV equal to IC by beta. IC already 20 by 20 milliampere by 2. This is take a 0.1 milliampere, or say 200. Okay, 0.1 milliampere. When you give this 0.1 milliampere to this, it will amplify up to 20 milliampere. We need to we decide to amplify this one, so that we need to set this RB according to this RB and RC, so that it can amplify from 0.1 milliampere to 20 milliampere, 0.1 milliampere to 20, if the beta is gain is constant. Okay, so here we need to find what is the RV value. RV equal to this RV equal to, we can find RV equal to, here from this equation, RV equal to VCC minus VBE divided by IB. Here VB equal to 0.7. For this I take a silicon, so that is 0.7 drop. VCC already know, 9 minus 0.7 volt divided by 0.1 milliampere. Okay, from this we get RB equal to 84 kilo ohm. Once we design fix RB equal to 84 kilo ohm, and this is 225 ohm. But some cases what happen now, that will sometime the beta will changes. If the beta changes, if this from this value only the skew point set here, if the beta changes now, then IC also again changes. Beta changes means IC changes, so that this one also changes, this one also going to change, so that it is not stable. It will not stable. In the fixed bias, this is the problem. So that in the next video we are going to cover some other biasing method, so that there you can control this type of problem. Thank you for watching this video. Please like and subscribe my channel. Thank you again.